Welcome to the course in Molecules in Motion. This lecture today we are going to discuss the various parameters which will be further required to be dealt with when we are doing or studying the transfer of ions or the properties transfer of charge through ions in various electrolytes and non-electrolyte solutions. So, what we have done so far is we have interpreted in the last class what is conductivity, which is also known as specific conductance. So, specific conductance was represented by kappa, and this kappa, as we have seen how that can be kappa can be related to the flux or a charge flux or J, or how it can be related with the applied electric field. We also discussed in the last class what would be the correct definition of a material which is following or obeying the Ohm's law. Ohm's law in general, whenever we say equal to V by I equal to R, is generally what we represent or say this is the definition, but this is only a definition. This does not prove, or this is not the statement for obeying a material obeying the Ohm's law. So, what was the definition which we put forward in the last class is a material is going to be said to obey the Ohm's law if it is conductivity is independent of the applied electric field E, or it is independent of the ion flux J. Okay. Ion flux is the amount of current passed through a particular window per unit area of that window. Okay. I by A is J. So, this is what the definitions we had put forward. So, still we are in the phase where we are defining various parameters which will be later used in our discussion. So, today is another such lecture where again we are going to discuss the various parameters which were utilized when we are talking about the conductance when we talk about the transport of ions in a solution medium. So, what we are going to look into today is the electrical conductivity of electrolyte solution. So, for that we want to calculate the charge or the mass deposited. For let us consider a electrolysis cell. See, you can see this is the electrolysis cell which is represented. You have two metals, these are the metal electrodes on each side, and the cell is filled with a solution which is known as the electrolyte. Okay. And potential difference is applied across the electrodes by connecting through a battery. So, this is the battery which we have connected to. Now, what happens when you are having a system where you have a solution phase as well as the solid metal electrodes? Electrons flow and take the current or carry the current through the metal wires. These are the connecting wires, and electron will flow like this. Now, it is the circuit does not get completed until you have something passing through the solution phase as well. So, you have this compartment filled with the electrolyte, and in this electrolyte ions are going to carry the current. So, and this is how the circuit is going to get completed. So, electrons are being carried through the metal wires and to the metal electrode which is connected to the metal electrode, and the ions in the solution is going to be carrying the current in the solution phase. Now, each electrode solution interface which you have this electrode, and each of this will have an interface in the solution medium. An electrochemical reaction occurs where the electron transfer is either to or from the electrode. If that is possible, see if the circuit needs to be possible, only if the solution phase is able to communicate with the interface through some electron transfer process, and that is what happens when you have an interface of metal and electrolyte solution. Either the electron is going to gain an electron from the solution, or it is going to take an electron from the solution. So, let us for example consider two copper electrode, and the electrolyte solution is copper sulphate. So, what we have the interface electrode solution interface reactions as, we have the copper ions in solution will gain 2 electron to become copper 0, and copper electrode will become lose 2 electron and become copper ion. Okay. So, this is how we have deposition of copper. So, let us see what we are looking into. We are trying to do some measurement. For this measurement, we are going to look into the definitions first. Okay. We know that the ions are going to carry the charge, or it is going to take the current through the solution. So, for measurement, what we are looking into is, we have a electrolysis cell in which we have a typical reaction where you have 2 copper electrode and electrolyte solution made up of copper sulphate. From this electrode interface reaction, what we can understand, how do we read this? 1 mole of copper to be deposited, if we have a condition where we want to deposit 1 mole of copper, what we require? We require 2 moles of electron that must flow through the circuit. Okay. So, if we want to deposit 1 mole of copper on the electrode, then 2 moles of electron must flow through the circuit, and 1 mole of electron is equivalent to 1 Avogadro number of electron. Okay. So, the 1 mole of electron is equal to the Avogadro number of electrons, that is 6.023 into 10 to the power 23. Okay. So, if current I, suppose the current I is kept constant, then the charge flow, what is the charge flow we have? Q by T is the current. So, charge flow is Q equal to I T. Okay. So, the current is given by the Q into equal to I into T. What is the I? It is the current which is kept constant into the time required for the deposition. So, experiments show, if we perform this experiment, experiments show that to deposit 1 mole of copper, the flow of how many charge is required? The flow of charge is 192970 coulombs. This is our experimental result. Okay. What we had interpreted? We have interpreted from the equation of the electrode and solution interface that 1 mole of copper to be deposited from the solution onto the electrode requires 2 moles of electrons through the circuit that needs to be flowing. Okay. And from our knowledge that 1 mole of electron means the Avogadro number of electrons, we have to, keeping that in mind, if the current is kept to be constant, then the amount of charge which is going to be required to deposit 1 mole of copper will be experimentally is found to be 192970 coulombs. Okay. So, the absolute value of total charge on 1 mole of electron is going to be 96485 coulombs. Why do we say the absolute value of total charge on 1 mole of electron? because we know experimental value, we have seen that experiment shows that for deposition of 1 mole of copper requires a flow of 192970 coulombs. And from the reading of the electrode reactions, we know that 1 mole of copper if it needs to be deposited, requires 2 moles of electron to flow through. So, if this is what we are going to got through experiment, if this is the amount of the charge which is required to flow for deposition of 1 mole, that means it should be equivalent to 2 moles of electron. So, if I want to find out what is the charge for 1 mole of electron, then this will be divided by 2. This is corresponding to the flow of charge which is equivalent to 2 moles of electron. This is what we have read, this is what we have interpreted the reaction to be. For deposition of 1 mole of copper, we require 2 moles of electron to flow through. So, if we do a experiment and see to deposit 1 mole of copper, what is the amount of flow of electron which is charge which is required, we will see that it is 19.2970 coulombs. From this, we can interpret the absolute value of total charge of 1 mole of electron. This is equivalent to 2 mole of electron. So, if I want to find out what is the 1 mole of charge equivalent to 1 mole of electron, then this will be divided by 2. So, this is what we get. The absolute value of the total charge on 1 mole of electron will be 9648485 coulombs. So, the absolute value of charge per mole of the electron, which is known as Faraday constant, is defined as F equal to 96485 coulombs per mole. Okay. So, the absolute value of total charge of 1 mole of electron we have interpreted or got from the experimental observation of how much charge is flowing for depositing 1 mole of copper. Okay. So, what we have to similarly, if we want to find out what is the absolute value of charge per mole of electron, charge per mole of electron, okay, where you have the Faraday constant equal to the Avogadro number into the electron charge, okay, or proton charge. So, we have this interpretation of Faraday constant, and Faraday constant, if I have to look into in absolute values, it is going to give me the charge per mole of electron. Okay. So, the Faraday constant is nothing but by definition is the absolute value of charge per mole of the electron. How much charge per mole of 1 electron, and that is given to be 9645 coulombs per mole. Okay. So, therefore, to deposit 1 mole of metal of say M, here it can be copper, from the solution containing Mz plus ions will require the flow of Z plus moles of electron. Okay. So, if I take this example, what do I get? To deposit 1 mole of the copper metal from solution containing the ions of copper plus 2 will require the flow of plus 2 moles of electron. This is how you read. Okay. So, for deposition of 1 mole of the copper from solution containing the ions of copper plus 2 ions will require the flow of 2 moles of 2 plus, or we can say 2 moles of the electron. So, the total from here what are the conclusions we are going to draw? the number of moles of the metal ion or metal deposited by the flow of Q charge. If the total charge is now flowing is Q, and the number of we want to find out the number of moles of the metal deposited, then what do we have? We are going to have the Q divided by by Z plus into F. Okay. So, the Q is the charge that is flowing divided by the what do you call this, the valency or the Z plus of the metal ion which is associated with into Faraday constant. So, suppose I want to look into this M being transferred replaced by a copper, then this becomes Q by, we know, so it is going to be 2F, okay, Q by 2F. Now, if we want to find out the mass of the metal deposited, then what do? We have this into multiplied this parameter multiplied by the molar mass of the metal we are looking into. So, Q by Z plus into F into the molar mass. So, this is the expression how it is going to look. This is going to be the mass of metal deposited, and with the mass being the m of the molar mass of the metal which we have associated with. Now, what we have initially talked about, that the total charge that flows through the circuit during time delta, say in some time delta t prime, is given by the integration of total Q. What is Q? Q equal to I t. So, if I have a duration of time and I want to integrate find out the total charge which is flowing, what do? I take for each interval of time and I integrate it over the period over which the charge is flowing. So, let the charge flow from 0 time to some time t prime during which the circuit is operative. Now, here we have said that the I is kept constant. So, I is going to be represented I, this is the current, into dt. So, with the change in time, how we are getting the total amount of Q, which is the total amount of charge that is flowing. So, if you look at this, if you integrate from 0 to t prime is the total time period which you are involved with. So, this is going to be integration of from 0 time to the time which of interest into integration of t into delta t. Since I is a constant, so the integration of delta t is going to give nothing but the t. So, what you have, the total charge that flows through the circuit during the time interval t prime is nothing but integration of the total charge involved, and that is equal to I t. Okay. Now, it is in this experiment what we have done, we have kept the current to be constant. Okay. Because of the current being constant, you are getting the total charge interpreted by that integration value coming to I t. Otherwise, if this had been a function, a variable, then this had to be integrated separately. So, but since we have kept the current constant throughout, we can just leave this as a constant and just integrate with dt, and that interpretation comes when you see that the total charge, total current is kept a constant. But it is not easy to always keep the current constant. So, there is another method which is usually when you are doing experiments, this is the method to find out what is the amount of the metal deposited, and that is known as the coulometer. A coulometer is a device in which you have an electrolysis cell which is in series in the circuit. What we do? We pass the current through the electrolysis cell and we measure the way the the electrode which is deposited, and from that we calculate m from the expression m equal to q m, that is the charge flow into m divided by z plus into f. So, applying this equation we can find out what is the mass of the metal which is deposited, right. So, these are the definitions which we are looking into, and how we can measure the charge. Now, we will go into much more fundamental definitions of various parameters, which we eventually will be using for our discussions on electrolyte and non-electrolyte. And for that, let us begin by something which we have already discussed previously, that is the conductivity or specific conductance, and before that we look into what is resistance and specific resistance. So, here we are looking into the conductivity of an electrolyte solution. Substance whose aqueous solution do not conduct electricity will be known as the non-electrolytes. For example, we have already talked about this, sugarcane solutions, glucose, urea, these are all salts which will the substance whose aqueous solution do not conduct electricity are known as non-electrolytes. So, these are the solutions which do not conduct electricity. So, these can be taken as examples of non-electrolytes. Now, what is resistance and what is the specific resistance? The fundamental measurement used to study the motion of ions is that of the electrical resistance R of the solution. So, for a conductor, if you see for a conductor of a uniform cross section length A and length L, see this is actually we can say this is A, this can be represented as capital A. What we have, see from this interpretation what we have, the fundamental measurement used to study of motion of is that of the electrical resistance R of the solution. For a conductor which is having a uniform length and uniform cross section area A, what will be the resistance? Resistance will be proportional to the length and inversely proportional to the area. Okay. So, if from this we can say R equal to L by A into a constant which is the resistivity. So, the rho is the resistivity or specific resistance, it is the resistance between opposite sides of a cube 1 centimeter cube of the conductor, and R can be equal to the resistivity when length becomes equal to the area, when L is equal to 1 centimeter and the area is equal to 1 centimeter square. So, this can be, this is the same A which we are looking here, and it is the same A which we are representing here. So, please make a correction, this is the A, this is the capital A, this is the capital A, this is the capital A. So, the capital A, if you have a uniform cross section area of a conductor and you have a length L between them, then the resistivity or the specific resistance is the resistance between the opposite faces of the electrochemical cell cube 1 centimeter cube container of the which is a conductor. So, we can say the resistivity will be equal to the resistance when suppose this is equal to 1, this is equal to 1, then the becomes equal to R becomes equal to rho. Now, another term which is important is the specific conductance. Specific conductance we have discussed in much detail in previous classes, but still just to go through what the definition is. Specific conductance is nothing but this is L by A into 1 by R, where resistivity which we have defined is equal to A by L into R, and from there we have the new definition. We can define what is kappa. This is the specific conductivity, which is represented by kappa equal to 1 by A into 1 by R, L by A into 1 by R. So, L by A into the conductance, see 1 by R is the conductance, is where L by A is nothing but the cell constant. Okay. So, units you have, just please take a note of the units. If you do not get the units correct, then the whole problem becomes wrong. So, the specific conductance unit is mho inverse, centimeter inverse, ohm inverse, centimeter inverse, or Siemens meter inverse. So, specific conductance is the conductance of a solution of 1 centimeter length having 1 square centimeter as the area of cross section. In other words, we can say the specific conductance is the conductance of 1 centimeter cube of a solution of an electrolyte. Okay. So, this is by definition what we have. Specific conductance is kappa by 1 by specific conductivity. So, this is how you represent it. Now, specific conductivity, on what are the parameters or factors on which specific conductivity depends on? Specific conductivity depends on the nature of solvent or solute, the concentration of free ions in the electrolyte, mobility of the free ions in the electrolyte, and temperature. So, the specific conductance is defined by the number of ions and their velocity and mobilities, which means the more the concentration of the ions in the electrolyte solution, more will be the specific conductance. If the mobility or the velocity of the ions are more in the electrolyte, then its specific conductor or conductivity will increase. Okay. So, another term which needs to be talked before we take up the various parameters in a electrolyte conduction is the equivalent conductance, and another one is the molar conductance. Equivalent conductance of ions produced when 1 gram equivalent of the electrolyte is dissolved in VCC of the solution. Okay. So, here we see in terms of the 1 gram equivalent ions of the electrolyte of the salt which is dissolved to form the electrolyte, where 1 gram of this electrolyte is dissolved in VCC of the solution. So, mathematically we can represent the equivalent conductance lambda equal to kappa into V. Kappa is what we have just now discussed about, which is cell constant into just a previous slide. This is the previous slide. This is the specific conductance, kappa equal to L by A into conductance, or cell constant into conductance is the specific conductance, and here we have a new term, equivalent conductance, which is nothing but the conduction by 1 gram equivalent of the electrolyte. So, if you represent that mathematically, then it is nothing but kappa is into the volume, and volume is 1000 per since we are talking about the gram equivalents. So, kappa will be multiplied by 1000 divided by the molarity, where kappa is actually the specific conductivity or conductivity as such. V is the volume of the solution. So, units can be represented as like this. You have the units of kappa, and then you have the units of the concentration. This way you can have the unit of lambda is as meter ohm inverse centimeter square into gram equivalent to the power half to the raised to the power minus 1, or we can have ohm inverse replaced by Siemens centimeter square into G gram equivalent to the power 1. This is how the dependence is, but I am not going to discuss this in right now. We are going only by the definitions of it. So, let us first finish off with the definitions. Another term is the molar conductance. See, molar conductance is the conductance of a solution containing 1 mole of the electrolyte in VCC of solution. It is represented by lambda m. Lambda m should be now, since we are not talking about molarity, we are talking about the we are not talking about the gram equivalent value or the normality, we are talking about 1 mole of the solution. So, we can say kappa into will be equal to kappa, that is the specific conductance into the volume of the solution V. That will give you the molar conductance. So, molar conductance can be represented previously in the discussion part. We can see that when we are talking about the molar conductivity is nothing but kappa, the specific conductivity, into 1000 by the molarity. The units of this you can look into. So, the relation between equivalent conductance kappa and the molar conductivity m, lambda m, is nothing but lambda m is equal to the valency factor or the n factor into kappa. That is how you are going to one is going to be specific conductance is going to look into the equivalent 1 gram equivalent of the electrolyte in VCC of the solution, and in molar conductance is 1 mole of the electrolyte in VCC of the solution. So, both needs to be kept in mind when we are talking about this. And what are the parameters which is dependent on? It is going to be dependent on the nature of electrolyte. Conductance of electrolyte depends upon the number of ions present in solution. Therefore, the greater the number of ions in the solution, greater will be the conductivity or conductance. The number of ions produced by electrolyte depends upon its nature. Concentration of the solution, molar conductance of electrolyte solution varies with the concentration of the electrolyte. In general, the molar conductance of electrolyte increases with decrease in the concentration or increase in the dilution. So, these are parameters which will be looking very closely when we talk about what various types of electrolyte which can be considered. The conductance of a cell will be conductance of electrolyte will increase with increase in temperature. So, we will look into the other forms of conductivities in the next class. Thank you so much.